Let's next see a necessary and sufficient condition for a linear operator to be unitary in theorem 6.10.1. So T is a linear operator on the inner product space V, which we already know is finite dimensional. Then T is unitary if and only if T maps any orthonormal basis of the space V onto an orthonormal basis of V. The proof starts like this. We first assume that T is unitary and then we prove that T maps every orthonormal basis of V onto an orthonormal basis of V. So for that we choose any orthonormal basis of V consisting of these n vectors Vi's. Now what is our aim? Our aim is to prove that the set of the images of these Vi's under T, that is the set consisting of V1T, V2T all the way up to Vn T, that set is also an orthonormal basis of V. In that direction, we first choose any index I lying between 1 and n and consider this inner product of Vit with itself. Because T is unitary, this is equal to the inner product of Vi with itself. But because this is orthonormal, so each vector has norm 1. That is, the inner product of any vector from here with itself is 1. So that way the inner product of Vit with itself is also 1. We also have this, that for any two indices I and j lying between 1 and n, we have written that in short like this. Okay, actually we should have written two separate statements, one for I and one for j, that 1 is less than or equal to I is less than or equal to n, and similarly for j. But you can write like this also, that has the same meaning. With I and j different, we next consider the inner product of Vit and Vjt, the inner product of the images of Vi and Vj under T. Again, because T is unitary, this is just equal to the inner product of Vi and Vj, and that is 0 because this is orthonormal. Distinct vectors are orthogonal to each other, and that is why, because of this fact and this fact, the set of the images of the Vi's under T, that is this set, is an orthonormal set itself in V. Note that we are not straight away saying that this is an orthonormal basis. We are coming to that next. And next we recall something from the theory of inner product spaces, that is lemma 444, which states that in an inner product space, any orthonormal set is linearly independent. By that result, this orthonormal set is also linearly independent. Now, because it is linearly independent, the vectors you see here, first of all, are all distinct. Okay, you cannot have repeated vectors in a linearly independent set. Actually, we are talking about a list of vectors rather than simply a set of vectors. But anyway, there are n distinct vectors here. So you have got a linearly independent set in the space V consisting of n vectors. However, you recall what we started with. We started with a basis for V having n vectors. That means V is n dimensional. And that is why, because you have found a linearly independent set of n vectors in an n dimensional space, automatically this is a basis from our usual theory of vector spaces. So that's how this becomes a basis for V. And because it is already orthonormal, so this is an orthonormal basis for V. So T has mapped the original orthonormal basis consisting of the Vi's onto another orthonormal basis. So this is one half of the claim. Now we are going to prove the converse. We start the converse like this. Conversely, let T map every orthonormal basis of V onto an orthonormal basis of V. Now we need to prove that T is unitary. And then we arbitrarily choose some orthonormal basis of V, say these Vi's, form a basis of V that is orthonormal. You do not confuse this one with the previous one, okay. This part of the proof is entirely different. We have started afresh. This is another part, it's converse actually. And what guarantees that V actually has an orthonormal basis? Well, that already is known from the theory of inner product spaces, that if you have a finite dimensional inner product space, then it has an orthonormal basis. You start with an ordinary basis, then you apply the Gram-Schmidt orthonormalization process to it, and then gradually you bring in new vectors, you weed out some vectors, and finally you get an orthonormal basis. You already know these things. Alright, so it is guaranteed that V has at least one such basis. Then by this very hypothesis of this converse part, this will also be an orthonormal basis. This is also one such basis. Now to prove that T is unitary, we arbitrarily choose two vectors u and w from our space. What is it that we have to show? We have to show that the inner product of ut and wt equals the inner product of u and w. Now because u and w are vectors in the space V, so each one of them will be a linear combination of the basis vectors. Say u is this linear combination where you of course have the vi's, the basis vectors, and with that some scalars alpha I, where alpha I is the coefficient of vi. I of course varies from 1 to n, and w is this other linear combination where the scalars are beta i's. Actually these alpha i's and beta i's you already know are in general complex numbers. So now we consider the inner product of u and w, and we use these linear combinations to write that inner product like this. You may notice one thing immediately, that here the index of summation is I, but here I have written j. The first thing is that I can write j in place of I because this is a dummy variable. So I can change its name, that does not change the sum. I can call it anything I want. But why did we do it? That is because we are now going to next write something else in place of this using properties of inner product. So what happens when you apply the properties or axioms defining an inner product? Linearity in the first variable, conjugate linearity in the second variable, those things. All the possible I and j combinations will appear here. So that is why I have used a different index of summation. And to save space, I have written only one summation symbol, although it's a double summation. I should have really written this one followed by this one. But this is a compact notation, you just have to understand what it means. Actually we have two sums, where I and j are both varying from 1 to n independent of each other. They are not influencing each other in their, when they are varying. So all possible I and j's come together and give us these terms, and we have this sum. And then we really use the fact that an inner product is linear in the first variable. So if you want to take alpha I, the scalar alpha I outside, you can. Okay, alpha I just simply comes out as it is. However, it is conjugate linear in the second variable, so beta j won't come out as it is, but rather its complex conjugate would come out. So that way, this is where you are right now. And now you recall that these v's, these vectors form an orthonormal basis. So that immediately tells you what these inner products are. If I and j are equal, then the inner product is 1. But if they are different, then it is 0. So many terms would vanish from this sum. So the simplification afforded by these values of these inner products, that is 1 and 0, leads to this. What happened here? Just now we said that those terms where I and j are different are going to vanish because these inner products would be 0. So that means we will be left with only those terms where I and j are equal. But being equal, I and j can be 1, it can be 2, it can be 3, all the way up to n. So that's how we have this sum. We don't just have one term, but we have a term corresponding to each such I and j where both of them are equal and they are say 1 or 2 or 3 like that. So this is how we finally have the inner product of u and w. But we also have these things. You recall the original expression which gives us u as a linear combination of the vi's, that is u equals summation of alpha I vi. On that, if you apply t and use the fact that t is a linear transformation, so that becomes this. T respects addition of vectors as well as scalar multiplication. So this is how you get ut itself as a linear combination of the VITs, the images of the VI's, the original basis vectors under T, and the scalars remain the same. Similarly, WT equals this linear combination of the VITs where the scalars are beta I. And then you also consider the fact that these images form another orthonormal basis, just like the original VI's form an orthonormal basis for the space V. So whatever we did just now with the original orthonormal basis and the linear combinations expressing the vectors u and w, we can do an exact similar thing with these vectors now. ut and wt with these available linear combinations, and also where the vectors whose linear combinations you are looking at here form an orthonormal basis just like those VI's form. And that's why I wrote like this. So an exactly similar calculation as above gives us this fact. What did we get there? That the inner product of u and w is this. Now the inner product of ut and wt will be this exact same thing. So that's why they are equal. So we write that fact here, that the inner product of ut and wt equals the inner product of u and w. That means T is an inner product preserving linear transformation. And coupled with this other fact that u and w were chosen arbitrarily from our space, this shows that this happens for any vectors u and w. And that just is the definition of unitary T. So that is why T is unitary. So here the converse part also has been proved and the proof is over.